Hi, my name is Ambrosio Valencia Romero. I'm an assistant professor of engineering management and systems engineering at Old Dominion University. I want to talk to you about strategic hindrances in digital engineering, in particular, the results from a simulation study of information exchange in a system of systems design problem. It has been said that a rising tide lifts all boats. Is that right? Well, consider three actors: Irene at the top, Jamie on the bottom left, and Kumar on the bottom right. Each of these actors is responsible for one engineering system. And these engineering systems may or may not be managerially or operationally independent, but oftentimes they need to work together. And in this collective effort, they also have figured out a status quo strategy. They have good knowledge of the systems and they know how it operates best. And they might not want to change that. Now, assume a promising new strategy emerges. And each of these actors have a chance to adopt this emerging strategy. Let's say this emerging strategy, this alternative strategy might be something like a shiny AGI, Enterprise Edition, or a guy instead. Now, we want to understand what would be the value of deviating away from the status quo strategy. Why would Irene, Jamie, and Kumar would adopt this promising new strategy? Well, oftentimes we assume that just because there is promise in this alternative strategy, that means that all of these actors will receive an increased value. They will increase their performance. So when we look at the value of switching that strategy, this is usually assumed to be a deviation gain. Sometimes though, it results in a deviation loss, as is the case now for Irene. Because of this expected deviation loss, Irene might not want to participate in this strategy. But this deviation loss can also be suffered by other actors like Jamie, Kumar, or maybe all of them face a deviation loss. So now we want to understand, okay, so what are the factors driving this deviation loss? What are the forces that affect strategic action in this collective system? And to do that, we use a device that we call the strategy dynamics. More information can be found in our work published in the journal PLOS ONE. So the case of interest of this presentation is digital engineering adoption. I'm not going to discuss digital engineering entirely in this presentation. What I can tell you is there is a growing interest in adopting a digital engineering strategy as part of a larger digital transformation. This is the interest of multiple sectors like defense, healthcare, public infrastructure, supply chain, and more. We want to answer the question, what strategy dynamics characterize digital engineering adoption? And we also want to understand how is such adoption affected by different resource allocation schemes. Now, where do we even start to answer these questions? We could run large human subjects studies, but that can prove very, very expensive. And because this is a socio-technical system, that would be the preferred approach, but we might not have all of the resources to run such a large scale study. But what we can do is we can model collective decisions and we can model collective incentives. We can leverage computational tools to do this. And what the way we call that is a collective system model. Let me give you an example of what that collective system model would look like. In this case, I'm going to use a bi-level system of systems design problem. More specifically, a surrogate aircraft design task. This aircraft design task has 4 design offices. One of them is fuselage, the second one is payload, then propulsion, and finally airfoil. Each of the design offices controls 3 design parameters, and all of them have to maximize a system level value, which is based on how far away they are from meeting the design requirements. Now, what would be the lower level decision? Because we're talking about a bi-level model of decision making. Well, in this case, we model the lower level decisions as first, local design search, and second, information exchange. Also, what would be the upper level decisions or upper level strategies? We focus on two strategies. One of them, which would be the status quo strategy, is peer-to-peer information exchange. The second one would be the adoption of an authoritative source of truth, the implementation of an ASOT. This would be a digital engineering strategy. Let's represent that using graphs. Now, here I'm only showing 4 out of 16 possible graphs. Why 16? Because we have 4 actors, we have 2 strategies. So 2 to the 4th, that is 16 possible combination of individual strategy outcomes, or that is 16 possible collective strategy outcomes. A key assumption here is that we assume that each actor's information exchange strategy will be set at the beginning and it won't change. Let's take a look at each of these scenarios. In this case, the 4 that we have in front of us. On the first column, we have peer-to-peer information exchange. At the top, we have all of the actors maintaining that status quo strategy. At the bottom, we have 3 actors maintaining the status quo strategy, while one of them deviates towards adoption of the ASOT. Now, here are the flow of design information. You see here that at the top left, we have that all of the actors will exchange design information between them, but after each design iteration, they would push that design information for synthesis. They will commit the design information to the synthesis node. At the bottom, we have that only 3 actors will push that design information directly for synthesis, while 1 actor will need to first send that information to the authoritative source of truth, and only after they have done that, that information will go for synthesis. Now, this authoritative source of truth will allow this actor, in this case Irene, to pull information that has already been committed to this ASOT. Let's go for the second column. In the second column, we have 3 actors adopting the digital engineering strategy, the yellow one, while 1 actor will remain at the status quo. Now, these 3 actors, by adopting the ASOT, they are able to pull information for that ASOT. So in essence, this would ideally increase transparency and it will increase the confidence in the information and the speed at which information is exchanged between the actors. After they have pushed that information to the ASOT, that design information can move for synthesis. But in this case, for Irene, they will need to request information directly from each actor separately, and only after they can go for synthesis. On the bottom right, we have a scenario in which all of the actors have adopted the ASOT. So ideally, this will result in maximum transparency in the maximum speed of information exchange. We label these scenarios. The first one is the status quo, while the one on the top right will be the lone holdout. The one on the bottom left will be the lone embracer of the ASOT, and the one on the bottom right will be unanimous adoption of the digital engineering strategy. Now let's talk a little bit more about the modeling of collective incentives. To do that, we use a model called a normal form. In this case, we use a normal form participation game. This comes from work in game theory by Dov Monderer and Lois Shapley. What are the key characteristics of this participation game model? First, these are potential games. I won't go into details about what that means, but what I can tell you is that they guarantee the existence of a strict equilibria. A strict equilibria, that is pure strategy Nash equilibria. What does that mean? For those of you who are not familiar with Nash equilibrium, what that means is these are points from which the actors or the players in a game will not want to deviate from, because it will result in deviation losses for them. So you can imagine that in the context of adopting of preferring a particular collective strategy, we would like to have the collective strategy to be first a strict equilibrium, and second, we want that strategy to maximize value for all of the actors, because there are strict equilibria that are not necessarily if payoff dominant. That is, they don't necessarily result in increased value for all of the or maximal value for all of the individuals. Second, these participation games use the Shapley value distribution rule. Some of you may have heard about Shapley values in machine learning, for example. This is a way in which we can measure the marginal contributions of a collective value by individual participants. So the way it is applied here is that it's done recursively with increasing participation of actors. Those actors that participate will receive a portion of that collective payoff they generate based on this Shapley value distribution rule. Those of you, I'm not going to go into details of how the Shapley value is computed, but what I can tell you about the Shapley value is that it has some nice properties that are associated to fairness. Because of that, and because participation games inherit these properties, these games are presumed to be efficient. Now, what would be the rules to assign individual payoffs in these participation games? How would we allocate these two to the end payoffs for these two to the end potential outcomes? So the first thing we do is that we will assume that the collective payoff that we will need to distribute using the Shapley value rule will be computed as the difference in value change in the in an scenario versus that of the status quo. In other words, we will track system level value across each iteration. And the difference between two iterations in one scenario, we will subtract will be subtracted to the value, the same difference in value in the status quo. It's a comparison between each of the 16 potential outcomes in the status quo, because in the status quo will also be part of that. That is, the status quo will result in a collective payoff of 0. Second, participating in the game will grant the player their Shapley value. That is, the collective payoff that is generated will be divided according to the Shapley value rule, and that individual payoff for each player will be allocated. So if, say, for example, in a strategy outcome, two actors adopt the ASOT, only those two actors will receive the portion of the payoff, which will be that difference between the status quo and the adopted strategy. So that collective payoff that they generate, that extra payoff or that loss in payoff, because that can be also the case, will be divided among the actors based on their marginal the marginal value that they can generate. Not participating will result in fixed cost. Now, this fixed cost, I'm going to assume that this fixed cost are zero for the sake of simplicity, but they can be anything. How do we model this, the lower level decisions in the context of each strategy? To exemplify how we can do this using a computational model, I'm going to bring two offices, fuselage and payload. Now, both offices have knowledge of the design. This knowledge I represent this knowledge as four boxes. There is a blue box for fuselage, there is a purple box for payload, a, a green a box for a propulsion, and an orange box for airfoil. Both offices have their boxes. The goal of local search for each of those offices is maximizing the value of the design, which would imply going from that Zeppelin-like design to one that looks more like an aircraft in the context of a simulation. And internally, all those design offices can only control their corresponding design parameters. So for example, fuselage can only alter length, diameter, and width location of the fuselage, while payload can only modify number of cells, charge, and location. Now let's assume that the fuselage office adopts the peer-to-peer information exchange strategy. So the way that this would work in a simulation context is that the fuselage office will send their information directly to the other office, and they will receive their information back from this office. As you saw, this was sending those blue boxes to the right and receiving the purple boxes on the left. Now, assume that the payload office adopts the digital engineering strategy, the ASOT. So similarly to peer-to-peer, in this case, it will be sending information to the ASOT. But now the payload office will receive copies of all of the information that the ASOT has stored. Regarding the design search, here I'm showing a representation of the local design space for each design office. We have three parameters. In this case, one of them is colored in blue. The other one is colored in kind of like a yellow gold color or golden. The other one is a color green. At the center, you see a red node, which will be the selected alternative. So the way in which the agents are assumed to search throughout this design space is that they will move each design space like a clock. So they will rotate each wheel basically, and that will change the red alternative selected at the center. Notice that this red alternative has 6 neighbors. So that means that the total size of the neighborhood, the space in which through which the design offices will search for a better alternative consists of 7 alternatives. The chosen one, the current one, and 6 more, 2 in each direction. Now, the total number of design alternatives in the search space will be 60 because it will be, in this case, the design parameter, the blue design parameters has 5 alternatives in total, the yellow parameters has 4, and the green parameters has 3. 5 times 4 times 3 is 6. This will be the size of the local design space. For the simulation, we assume that the players search throughout the design space using a greedy search. And they will do this 50% with an allocation of 50%. We use a random process generator, and in this case, there is a 50% probability that in this iteration they will do local search, and 50% probability that in this iteration they will perform an information exchange. Now, this information exchange will be random. So if they have selected a peer-to-peer strategy, it will random between the agents. I mean, so they will randomly pick an agent with whom to exchange design information. And in the case of a full adoption of a digital engineering strategy, I mean, that will be just that. They will just exchange information with the HSOT. Now, again, global design value will be measured based on the proximity to requirements. And in terms of how long the simulation runs, we run 60 design iterations, 60 major iterations, and we do this 1,260 times per each scenario. So each of the 16 possible collective strategy outcomes is run this 1,200 times. Each of them has 60 iterations. Now let's take a look at the simulation results. Again, this is a simplified collective payoff, a simplified formula for the collective payoff. Here I'm showing you 4 rows of results. In total, there are 15 results. I'm not showing the status quo because that's going to be 0, but here I represent the status quo as the reference using that red dotted line. That will be our reference point. At the top, we have the lone embracers. You see that each a plot has 4 boxes at the top or at the bottom. Each of those boxes represents the strategy that the offices will have selected. In the case of the lone embraces, we have only one box in yellow. That is only one design office who have adopted the authoritative source of truth. In the second row, we have the adoption divide. These are the scenarios in which half of the actors would adopt the digital engineering strategy, the other half will remain with the status quo strategy, the peer-to-peer information exchange. The third row is the lone holdouts. This is the scenario where one actor remains at the status quo, the 3 others adopt the digital engineering strategy, and at the bottom we have the unanimous adoption. Let's take a look at some of the results here. You see here that with the lone embracers, the best performance takes place when the design office number 1, that is fuselage, adopts the digital engineering strategy. Whenever the other offices are the lone embracers, the performance is lower. So in this case, all of them are losing with respect to the status quo, but that loss is minimized when the design office number 1 is the one adopting the alternative strategy. On the second row, we have the adoption divide, and we see that the best performance is achieved when actors 1 and 4 are the ones adopting the HSOT. For all of the other cases, there is a dip in performance with respect to the status quo. On the third row, we have that the best performance is when 1, 2, and 3, that is fuselage, payload, and propulsion, adopt the strategy. However, I want to highlight something here. Notice that when it's 3, the one that is the lone holdout, that is the only one remaining at the status quo, there is a slight increase in performance. Same when actor 2 is the one remaining at the status quo. Conversely, when actor one doesn't adopt the digital engineering strategy, there is a significant dip in performance. Now, you can imagine that it seems that whenever actor one is a participant, whenever actor one is involved in the digital engineering adoption, the adoption of a authoritarian source of truth, there is an increase in performance for that strategy. So if we were looking at unanimous adoption, you could expect that, or you would expect that actor one will get the largest piece of the division of the collective payoff. And that's what the Shapley value does. That's what the distribution rule does. Let's take a look at that. So let's enhance this. And now let's compare these individual payoffs with the collective payoff divided by 4. So the way the Shapley value distribution rules operates is that in this case, it will uh, a, a, it will give the larger impact to those that have the better standalone performances, and those that have a larger marginal contribution. So those that will join, that will participate of adopting the digital engineering strategy will have the higher uh, portion of the collective payoff. See here that that's the case for office number 1, followed by office number 4, airfall, and then we have that offices number 3 and number 2 are at the bottom of the pile. Their individual payoff will be below the average. Will be below, but that splitting the collective payoff in 4. So with these results, what strategy dynamics characterize digital engineering adoption then? Our first research question. So to answer this, what we do is analyzing the emergence of a strict equilibrium. Now, here is a summary of that analysis. I'm showing here the pure Nash equilibria in red, and there are 16 rows. The one on the top is the unanimous remaining in the status quo, unanimous status quo strategy. And you see that there is a pure Nash equilibrium there. Almost all of the iterations result in a Nash equilibrium. This means that this outcome is very stable. This implies that it might not be it might be unlikely that the actors would deviate away from the status quo. Also, it's shown that the loan embraces wouldn't be sustainable in that regard, because of those single deviations will most likely revert back to the status quo. At the bottom, we also see that unanimous adoption of the digital engineering strategy results in no equilibrium at all. However, we do have some, in between outcomes that look good enough. For example, the third to last row, the case in which the design office number 2, that is the one that was the lowest performance, the lowest performer, whenever they remain at the status quo, not only we have an increase in performance, but we also have a stable outcome. Now, let's ask, can digital engineering do better than this? So to do this, I'm not going to go into details, but I can tell you that we believe the answer is yes, but there are some things that we will need to address. The way we come up with such an outcome is by performing a correction of the strategic hindrances, but this correction needs to be done in a way that it balances the fairness, the conditions of fairness, and the efficiency. Now, if we do that, you see that we have the emergence of equilibria for the unanimous adoption of the digital engineering strategy. The way this correction works is that we do a reallocation of the fixed cost. So this reallocation, remember I mentioned that the fixed costs were assumed to be zero. So this is what I mean, finding a balance between fairness and this efficiency. Because of the cost, the sum of the cost needs to be zero. That means that this reallocation basically results in some value being transferred from some actors to others. But again, I have to do it in a way that it maintains the differences reached by the Shapley value distribution rule. There's also trade-off in doing that. And this trade-off is the emergence of biostability conditions. So I want to point out there that more equilibria is not necessarily a good outcome, just as is no equilibria at all. So we want to have a compromise between those two. And in this case, we have now two equilibria that are total opposites. What can we do there? These are called biostability conditions. The good thing is that when these conditions emerge, we can use methods of risk dominance. We can analyze what of these two stable outcomes would be risk dominant. That is, which one would be preferred in terms of risk. And we can find ways in which we can measure that and understand how likely it is that the actors adopt one or the other, assuming, of course, economic rationality. And this is a hint at an answer to research question 2. Recapping that question, that is, how is digital engineering adoption affected by different resource allocation schemes? So here what we did is that we reallocated the collective payoff. We did not add extra value. We just did, apply the Shapley value distribution rule, but then we look back at the fixed cost and we try to reallocate them in a way that it will keep the sum at zero. This is a zero-sum cost reallocation rule. Now, what are the insights of this work? What did we learn? So, and this is specific to this problem, of course. We learned that this method can help us identify which systems are most critical for adopting a new strategy for information exchange in the context of systems design. Of course, once we change the problem, we will need to revise our assumptions of desirable strategy outcomes, and there will also be different emergent strategy dynamics. A second insight is that we saw that a zero-sum cost allocation rule can be leveraged to find this compromise between fairness conditions and strategy alignment. We want to facilitate the conditions for a specific strategy to be unanimously adopted, the digital engineering strategy. But we need to be mindful that we need to also maintain economic fairness as it is defined through the Shapley value, but also we want to make it in a way that we are not messing too much with the allocation of payoffs. And one potential use that this has is that we can use it for the design of network topologies. So we can apply this to network systems to see what best network configurations would improve a value, collective value and individual value at the same time. Now, this study is a pilot. I mean, we will need to incorporate a more detailed description of the strategic behavior in sociotechnical systems and systems design, and we will need to take a closer look at the lower level decisions too. But we believe this is a good starting point for applying this methodology to other systems. Now, we need to acknowledge what are the limitations of this study are. And very importantly, one limitation is that we need to verify, we need to assess the representativeness of this work in the context of digital engineering, right? This is still a toy problem. This is a proof of concept, and these results may not extend to digital engineering in practice. So we need to be mindful of that, and we need to keep working on making sure that our models and our results are more representative of the application case. We also relied on oversimplifications of operational decisions. In particular, we assumed that information exchange was uniformly distributed. So we assumed that that process was used to the uniform distribution. That the operation of the information exchange operations were followed this uniform process generator. Now, we also assume greedy local design search. That is, every time the actors wanted to maximize system value, they will choose the one that will maximize the value in their immediate neighborhood. We could have implemented simulated annealing. We could have implemented reinforcement learning, but we wanted to keep it simple. The other assumption, and this is a limitation of the work, is that we are assuming one-shot strategic decisions. As I mentioned, we are assuming that the actors make their strategy selection at the beginning and they don't change that selection. Another limitation is the computational complexity of this work. As we model more actors and more decisions, this problem just grows in complexity exponentially. So the problem might become intractable. And it also can become cognitively intractable. But in terms of cognition, maybe to do that, we can do some AGI. Oh, not that one. Thank you so much for your attention. I look forward to your questions and comments. Have a good one.